Special relativity is a theory regarding the relationship between space and time. It was proposed by Albert Einstein in 1905 in his paper on the electrodynamics of moving bodies. Einstein put forward this theory to correct the problems that arose due to the inconsistency of Maxwell's equations of electromagnetism. Maxwell's equations were invariant under the Lorentz transformations. The Lorentz transformations are coordinate transformations between two coordinate frames which are moving at a constant velocity relative to each other. Mechanics that handle situations involving motions at a significant fraction of the speed of light are corrected by the theory of special relativity. Special relativity is comprised of two main postulates. 1. The laws of physics are identical in all inertial reference frames. 2. The speed of light in a vacuum is the same for all observers. The speed of light is the same in every inertial reference frame. The word special and special relativity really means special case. This explains why special relativity differentiates from general relativity, as it only applies to specific situations where different frames of reference are not accelerating. These are known as inertial reference frames. Scientists know that no matter how fast you're traveling, the speed of light is constant for everyone. If John is standing still on Earth and Sarah is moving in a spaceship, they will experience light at the same speed, i.e. 300 million meters a second. In order for this to happen, they must both be experiencing time in different ways. Time is relative to the speed at which John and Sarah are traveling. The phenomenon of time dilation dictates that John, who is stationary, will view the time on the spaceship as being slower than the time on Earth. Sarah will see her time as being normal. If Sarah was traveling at the speed of light and had a light beam bouncing up and down in the spaceship, she will only notice the vertical component of the movement of this light beam, and it will move fast. If John is viewing the same beam from Earth, he will also notice the horizontal movement of the beam due to the acceleration of the rocket ship. Overall, this gives the light beam a diagonal motion, which takes longer to complete. The faster something travels away from you, the smaller it appears. So if Sarah is traveling in a spaceship at 150 km an hour, the spaceship will appear normal size to John and Sarah as it moves away from the Earth. If the spaceship is traveling at half the speed of light, it would appear much smaller to John. However, to Sarah, the spaceship will appear to be of normal size, clearly showing that the phenomena of time dilation and length contraction are intertwined. The effects of length contraction and light time dilation are negligible at everyday speeds. The amount of energy that an object has, its inertial mass, increases as an object gets closer to the speed of light. This means that a greater force is required to increase your object's speed even further. This explains why no object that has an inertial mass can go faster than the speed of light, as an infinite amount of energy would be needed to do this. This can be a problem for space travel, as it becomes harder to travel at higher speeds. GPS satellites that are in orbit around the Earth also experience time dilation due to their high speeds, meaning the satellite clocks have to be programmed with correction factors to account for relativistic effects and remain in sync with Earth. The time dilation equation is used to program the clocks on the satellite to have the correct time. Planes can also be affected by time dilation, but only by a very small factor, roughly a few billionths of a second behind the other. If the younger child from a pair of twins was to leave Earth for 20 years on a spaceship traveling at speeds near the speed of light, when they returned they would be younger than the twin who stayed. The age difference can be determined by how fast the ship was moving.